Let me move the test bench here. So the inputs to the priority encoder are the following. There is a array called IRQ in, and it has as many bits as there are. Okay. So we have declared number of input interrupts as a parameter. Okay. So a parameter allows you to sort of generate an IP. This is called as an IP. IP means intellectual property, right? So if you are a company that is generating some sort of an intellectual property, right? See, you may want to write it in such a way that when you sell the same IP to multiple customers, you can customize as per the needs of the customer, right? So imagine that you have developed a new multiplier of some kind, right? So it is an M cross N multiplier. Maybe you want to customize that multiplier for as per the needs of the customer. So your N and M can be parameters. So here the number of interrupts is shown as a parameter, and this is a default value. That means if it is not set, it will be taken as 8. Okay. So normally when we instantiate this priority encoder, so here I have instantiated the priority encoder. I'm sorry, here I have defined the priority encoder. Here I have instantiated it. Right. At that time, I can declare the number of this value number of interrupts. Okay. So the default was 8, but here I have set it to 16. I can set it to whatever value I want. Okay. And there are two outputs. So we are receiving several interrupts, and we will produce one output, which is a 1-bit output, if any one of them is interrupted. Okay, this is an information for the CPU. The CPU knows that somebody is interrupting. Okay, and CPU also needs to know who is interrupting. So that is an ID. Okay, acknowledgement ID. So the CPU would acknowledge the interrupt of that particular interrupt which has highest priority. And we have decided that 7 has the highest priority, 6 has the next higher priority, and so on. So in other words, higher the number, higher the priority. Okay. And if there are n inputs, n interrupts, then the ID of the processor will have log n bits, isn't it? It will have log n bits. So suppose the number of interrupts is 16, then the number of bits in the ID of the interrupt device, right, will be 4, right? 0, 0, 0, 0, all the way up to 1, 1, 1. Right? So we have to use this built-in function called $C So C-log2 means the ceiling of the logarithm to base 2. Okay? So for example, if n is 15, okay, then C log 2 to the base log to the base 2 of 15 will be approximately 3 point something. I don't remember how much it is. So C log 2 will be the next higher integer. It will be 4. Okay. So in this example, we have set it to exactly 8. So C log 2 will return 3. Okay. C log 2 of number of interrupts will return 3. So 3 bits are enough. Okay. So it is a minimum number of bits required to represent numbers in the range 0 to n minus 1, where n is the number of interrupts. In order to implement the priority encoder, we have first generated the acknowledgements. Okay. So we keep some registers, okay, as many as the number of interrupts, called IACK. IACK will be 1 if the interrupt is acknowledged. So remember that exactly one of the interrupts will be acknowledged. And we will need this higher interrupt a little bit later. Okay. To check whether anybody is interrupting me, all I need to do is take the logical OR of IRQ in. Okay. So this syntax means take the logical OR of all the bits in IRQ input. Okay. So if none of them is interrupting, this output will be 0. If at least one of them is interrupting, this output will be 1. Then this is the behavioral model of this interrupt request or a priority encoder. Okay. So remember always. Okay. So always means usually with always we provide a list called sensitivity list, right? So which means that if any one of them interrupts, okay, if anybody changes their status from 0 to 1 or 1 to 0, this will be evaluated, right? Then initially in the first loop, we are going to do the acknowledgement. Okay, we are going to compute the acknowledgement. So we are starting from the highest interrupt. Number of interrupts -1 to all the way down to 0, because we would like to acknowledge the highest interrupt first. Okay, so we have to go in the order of number of interrupts -1 all the way to 0. So we are keeping this Boolean variable to check if anybody above me is interrupting. Okay. So what we do is we go from I plus 1, okay, all the way up to number of interrupts. So I is currently, let us say, let us assume that there are 8 interrupts. So we are going from 7 down to 0. So let us say we are looking at the 5th interrupt. Let us say J has become 5. Then we have to check for 6 and 7. Okay. For example, if we are in the last one, let us say J has become 0. Then I'm sorry, I has become 0. Then J will go from 1 to 7. Okay. What we are doing there is initially higher interrupt has been set to 1, right? We will AND it with not of IRQ in J. That means if when it comes out of this for loop, what we'll compute is IRQ for the case of, let us say, I equal to 5, we'll calculate IRQ 6 bar dot IRQ 7 bar. That means neither of those are interrupting. None of my sort of interrupts above me are interrupting. So in that case, I will take the interrupt. So if nobody above me is interrupting, and if I want to interrupt, then I will become 1. All right. So once we have calculated the acknowledgements, the next phase is to decide, how to generate the ID. Okay. So for that, what we are doing is we are setting all these bits. Remember, I told you that the ID will have log 2 to the base n bits, right? So we are setting each of those bits. So initially that bit is set to 0, and then we go and check. See if there are, let us say, if n is let us say 8 or something like that, then we need to set 3 bits, right? So first we start with 0, okay, and check all those numbers where this bit has a 1 in that position, okay. So that happens to be all the odd numbers, okay. So we'll check at 1, 3, 5, and 7. Then we'll check for the second bit. So there the numbers are 0, 1, 0 is 2, then 0, 1, 1 is 3, then 1, 1, 0 is 6, and 1, 1, 1 is 7. Last but not the least, we look at this bit. So there the numbers are 4, 5, 6, and 7. Okay. So that is what is happening here, right? At the end of this loop, we will have calculated the ID of the interrupting processor. Okay, and yeah, anybody has any doubts? All right. So let's move on. See, in the first class, I had mentioned to you about what is design verification, right? I told you that it is also called functional verification, and I told you that it is done in order to compare the specification and the implementation, and to point out if there is a deviation from the specification, right? The other two terms that we use are validation and testing. Okay? So validation and test, right? So you must understand the difference between these three terms. I have already explained to you what verification is. So validation is, see, when you get your chips back, okay, when you make the first samples of the chip, right? See, normally after the design is completed, after the complete design flow has been all done, right? When we are ready to manufacture, right? Only a few samples are made, and then those are first subjected to what is called as validation, right? Because we have made a product, okay, with certain assumptions, right? We had made some assumptions about the market, right? We, we had made some assumptions about what kind of performance we are likely to achieve, right? The proof of the pudding is in the eating, right? So we have to, we can, when we start cooking, we may have some lofty ideas about how we are going to make the best cake or something like that, right? Only when we finish baking the cake, we know how it looks and whether it looks all that grand and all that, right? So when the validation phase occurs, what is really done is they make a lot of measurements. Okay, if it's an analog chip, for example, let us say it is some sort of a analog to digital converter or something like that. See, there are many specifications for the A to D converter. There is, integral nonlinearity, differential nonlinearity, etc. Then, if it's an operational amplifier, you may have very many, specifications like gain bandwidth product, offset voltage, and so on and so on. Even if it's a digital processor, you may have a number of specifications such as what kind of bit error rate you are able to achieve, what kind of throughput you are able to achieve, what kind of performance you are able to achieve with that processor and things like that, right? So when we actually go and get the silicon and sort of usually we may want to make a small system, okay? So it's like a test, okay? Just like we created a test bench just now, right? It's a very small, minimal system that we can use to sort of test our product that we have designed, right? And when we do that, we are going to be honest and see whether we have achieved what we wanted to achieve. Okay? Suppose it turns out that we are not getting all those performance parameters right? So then we don't want to rush and start making this chip, right? So it is something like I gave you the analogy of the book earlier, right? So when we are only looking at the manuscript, right? Suppose I have PDF files that I have received, right? And I can see there are several chapters, right? And I on the when I look at those PDFs on the computer, it looks very good, right? Very beautiful color pictures are there and all that, right? Um, then when I go and make the first copy, right? One or two copies I make and I examine. See, there is a slight difference between what we see and what we get. Okay, whether the book prints exactly the way we think it will print, right? And the book may be actually a smaller in size than what we see on the screen. So there is a little bit of a disparity, right? And when we look at it, it may not look as attractive as you thought it would, right? There are no color pictures; it's all black and white, right? And maybe you start realizing that maybe you should have taken certain permissions, things like that, right? So there are some red flags. So you don't want to make a lot of copies of this book without overcoming those blocks, right? So that is what validation is. So validation is a way to look at the samples, run a lot of tests on the samples, um, and see in the system what does it do? Does it really do whatever we thought it would do? Right? And in the validation engineers, right? They sort of may connect with all the others in order to clarify their doubts. If they are not getting the right performance, etc., they will perhaps go and talk to all the designers, right? Physical designers, everybody, right? And try to understand whether they are making a mistake in using the system in some way. So finally, the answer is whether we should go ahead with this or not. Okay. So validation engineers may give the green flag. So, I am satisfied with this product. I think we should go ahead and ramp to production. Right? Only then, it will be made in large number of copies. Okay, is that clear to everybody? What validation is? Some people call it post-silicon validation. So now the mass manufacturing has happened, right? So we are not, we now don't have one or two. We have millions of them. Okay, just like in the book example, maybe many copies of the book were printed. Maybe thousands of books were printed. Right now, unfortunately, they may not work. All the chips that we have made may not work. Why? We had done a perfect job of design verification, right? Why would they not work? So again, look at the analogy of the book, right? We had read the book from cover to cover. The manuscript was read very carefully, right? All the typing errors were corrected, right? Everything was done the way it was supposed to be done. Then validation also we did, right? Now, when many copies are printed, unfortunately, you may have also come across, right? In when you purchase the book, some pages are missing, isn't it? Some pages went missing, or the same page is repeated, right? Or mm, maybe one page was printed inverted, isn't it? I'm sure we have all seen this, right? So it is a problem now, right? So how do you, as a publisher who has millions of these, no, may not be millions, maybe thousands of these copies in your hand, right? And you need to ship them across to different parts of India, or even different parts of the world, right? See, you can't sell, you know, um, books in which pages are missing, right? What will happen if you do such things? If you sell books in which pages are missing or pages are inverted, some the pictures are not at all visible, it's all smudged. What will happen? See, your reputation is at stake, isn't it? People will start saying, this particular publisher, publishes very poor quality books, right? They may not be making a comment about the content of the book. The production is very poor quality, right? So as a result, the publishers will not like to sell such poor quality books. Okay, so our quality control has to be there, right? So you are right. I mean, somebody said customer satisfaction, etc. That's correct, right? So see, now the problem there is, why did it happen? Why did this page get inverted, or some pages went missing, some pages were blank, etc. Right? These were not because the design was wrong. The design was good, right? But something went wrong in the production. Something went wrong in the manufacturing. Okay? Because manufacturing is also, it is a process, isn't it? There are printers that are printing, right? And then binders have to do their binding. So there are a lot of people who get involved in the production, right? And if there is any sloppiness somewhere and it's not properly controlled, the process is not controlled properly, we'll end up with these kind of problems. Okay. So the problem now is, we have to decide, which are worthy of selling, which books are worthy of selling, and which must be discarded. Okay. Suppose we have printed 1,000 books, okay, 1,000 copies, and we find that about 20 have come out really badly, right? So we can, discard them. We have to throw them away, right? The remaining 980 or whatever, they are worth selling. Okay. In fact, even there you can distinguish. See, maybe some are have come out really very beautifully because the colors were all very sharp, etc. Some are not so good looking, etc. So you can create multiple bins, right? And you can price them slightly differently, right? Maybe you have a market in other countries, and you are willing to send more expensive books there, right? Whereas the cheaper ones you can sell here, things like that, right? So that is called testing. Okay, in testing, all the chips that have been fabricated had to be individually checked. Okay. So imagine going through a book, every page of the book, right? Turning every page of the book and making sure that nothing is inverted, nothing is duplicated, etc., etc. It's not easy, right? It takes a lot of time to do each of those, right? I had to employ a lot of people to do that, right? And the more chips I make, the more costly it will become. You agree with me? So testing is what is called as people refer to this as production test. Whatever I just described is actually production test. So the it is done post silicon. It is done post silicon, and when we have ramped up to make large number of chips, right? At that stage, we have to ensure that we are rejecting bad chips, and we are maybe classifying these chips as maybe high performance. Some of them will give you very high performance. See, maybe you made a microprocessor to work at 500 megahertz. There will be chips that will work at even slightly higher than 500 megahertz. Then there will be chips which will work at 500 megahertz, and then there will be chips that work at 400, right? Maybe it's okay. You can sell them in a different market where they may purchase, even if it is slightly lower in price, lower in performance, right? And those which are outright bad, okay, they have to be discarded. So testing is an expensive thing to do. Same is true with validation. Same is true for design verification, right? So design verification, as I mentioned to you, the statistics is that about 70% of today's expenditure in making a chip goes in design verification. Okay, it is one of the most expensive phases, right? Testing is also similar, right? Usually the testing cost is given in how long it takes to test. So, like in the example of the book, right? If the book is, let us say, 1,000 pages or 500 pages, right? Then you really have to go through all of them, right? You don't read everything, right? You're not going to read the all the pages, but you're going to flip through to see if there is anything really bad, right? So the bigger the chip, it takes longer to test, and as a result, the cost will be high. So is that clear now? These are very different activities. Okay. Unfortunately, people confuse. Okay, when they mean verification, they say test and things like that. So is that clear to everybody? Any questions? Fine. All right. Let us continue our discussion. Right. Um, Let me suggest a somewhat game like a I'll give a sort of a fun example, right? Imagine that you have to play a game, right? You may have played this game before, right? See, suppose I guess a four-digit number. Okay. So let us, and the thing is, it should not have repetitions. Okay. Let us pretend that I have guessed 4, 5, 6, 7. Then I will ask you to guess the number that I have kept in my mind. Okay. So you don't know this number. Okay. So let us say you come back and think, you tell me that, it may be 1, 2, 3, 4. Then I'm going to tell you something to help you guess better. Okay. 1, 2, 3, 4 is not the correct answer. I will say 1 is not there anywhere. Okay. So I'll say minus. 2 is not there anywhere. 3 is not there anywhere. 4 is there, but 4 is in the wrong place. Okay, so I can sort of tell you that either you print it in color or something like that, or you can say C means cow. Okay, so when they say the C, they know that 4 means the 4 is not in the right position. It is there somewhere. So based on this, they can improve their guess. Okay. So 4 is there. So we can try maybe apart from 1, 2, 3, we can try maybe 5, 6. Okay. 5, 6, and maybe 9 or something like that. So they may guess 9, 6, 5, 4. So this time you will say 9 is not there. 6 is cow because it is there, but not in the right position. Then 5 is uh, there, but in the wrong position. 4 is okay. The person who possibly he will give 9, 4, 6, 5 because he already knows that 4 is not in the right position. Okay. So this time the answer may be 4 is still in the wrong position. 6 is in the right position. So it's a bull, right? And 5 is also a cow. Okay. So now people will know that 4 is different. I mean, 4 is there, 5 is there. The other numbers that they have not tried are 8, for example, right? So we can try maybe bringing uh, 4 to this position, right? And maybe we'll bring 5 here, and then 6 here, and maybe 8. Okay? So this time I'll tell them it is bull, 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 and minus. Okay? Now I think the only number that you have left is possibly 7, right? I think we have tried all the others. So this time that person will guess B 4, 5, 6, 7, right? And he will get all correct. So if we get all 4 bulls, then the answer is correct. Okay, he won the game. Okay, so let me I'll keep a number. You try guessing. Okay, one of you give me a guess. Any 4-digit number you can type in the chat, and I will. Any 4-digit number you can type. Sorry, I'm not looking at all. Okay, let us look at Amiya. Okay, so Amiya, let me I am I am telling you I have this is the feedback for you. Okay. So you tell me a better guess. Only Amiya, please type. So based on your guess was 6, 7, 8, 9. Okay. So based on your guess, I have given you this feedback. So what will you say? What will be your improved guess? Anybody else wants to help Amiya? Okay, somebody Atharva Savant is saying 1293. Okay. So my feedback to Atharva will be so that means both 9 and 3 are there, but in the wrong position. So Atharva Savant, you try. Okay, somebody said 9345. Okay, Mihir Patel. So Mihir Patel, you have hit the jackpot. Okay, so this is the answer I have given you. I'm sorry. Uh, I think he got the answer. Okay, so by chance he got the correct answer. This was my 9344 is correct, right? But you got the idea, right? Everybody understood the game, right? So, and there will be a certain number of trials. Okay. So we can give them maybe 4 or 5 or 6 trials within which they have to guess, right? And that is the game, right? So if you think about it, okay, what are the things that we have to do in this game, right? First stage is we have to read the input. First thing is to guess the out, create a or get what do you call it? Secret, generate a secret number. Okay. Then we have to read user input. So the user has to somehow enter 4 digit. Okay. Then based on the user's input, we have to give the feedback. Right? And if feedback is all B, then we are done, right? We can also keep other things like maybe guesses. Okay. Initially, how many? Let us say max guesses is 6 or something like that, right? Read user input and guesses equal to guesses minus 1. Okay. Then if feedback is then write congratulations, etc. Right? Otherwise, uh, check if else check if num guesses is greater than 0. Okay. If so, continue. Else else write sorry, better luck next time, etc. Something like this. Okay. So we can easily write a program in C language or Python or something like that to do this, right? We can also maybe do this in hardware. Okay. There is a very similar game that many people play online. Anybody knows what this game is? It is very similar, very popular. It's called, it is from New York Times. Wordle, very good. Anupreksha has guessed it correctly. So Wordle is here we are not going to do Wordle because it's difficult, right? In Wordle, when somebody writes a word, see in Wordle, people guess 5 letter words. Okay. So maybe I have kept a word in my mind. Okay. It's called delay. So I'll ask you to enter a 5 letter word. Okay. So you may try something, let us say, mm, let us say you try ovens. Okay. Then I will tell you O is not there. So O will be printed in black. Then V is not there. E is there and it is in the wrong position. So it will be printed in yellow. Okay. Then N is not there, black. And S is not there, black. So this will be printed in a yellow font to just say that, this is in the right position. It is, so based on this, we can improve. Okay. And so on. Here also I think they give you exactly 6 trials. Okay. If you can't guess it in 6 trials, you're out. Right. So this is the game, right? So what do you think is the most challenging part? Okay. See, generating a secret number, maybe we will figure out some way. Okay. We'll figure out some way. Later in the class, maybe we'll talk about that. This is not such a big deal, right? Reading the user input also, well, it's not trivial. You have to think about how to get the user input, whether you will read it from maybe some hmm, maybe it is some switches or something like that, or there is a keyboard, right? Something you have to think of, right? I'm imagining a hardware here. Huh? This is not a software implementation. Okay. I'm not asking for you to write a program. Okay. It's a hardware verification, right? And all these we can somehow write. Okay. These guesses equal to this. These are all okay. Which do you think is the most complicated one? I think this part is the hard one. You agree with me? Giving the feedback is the hard one, right? So how do you give feedback? Okay? So given, let us say this was my number 4967, and you gave, let us say, 2359, right? So I'll have to go through this list. So 2 is not present. So it must be minus. 3 not present, minus. 5 not present, minus. 9 present, but in the wrong place. So it is a C, right? So we have to implement some hardware for generating this feedback. So that is our challenge. Okay, so how do we do it? How do you develop a hardware for generating this feedback? Okay. How do you accept the input and how do you generate the feedback? So what does they mean in temporary register means what, man? So Jainil says you can put a four keyboard. Yeah, that's a good idea, right? Okay. So we have to write a module, right? So we have to decide what are the inputs and outputs. So module check, or, generate feedback or give feedback. So what will be the input and what will be the output? The input is maybe 4 digits, isn't it? We have to give 4 digits, right? So how do you say that? Let us say in digits or user guess. So, or user guess. So that is one input. And maybe the other thing is we'll assume that it's always 4 bits. I mean, we'll not make it complicated by trying to change the number of digits. Okay, we'll assume that the number of digits is always same. Number of digits equal to 4. So given a 4-digit number with no repetitions, we'll assume this. Okay, there are no repetitions. Generate a feedback string of 4 entries. So feedback string is equal to either minus or C or B, right? So C minus if uh, user guess um, feedback string of I. Okay? So if user guess of I is not in user guess, I'm sorry, not in the secret. It is C if user guess of I is in secret, but it is in the wrong position. Finally, B, if user guess of I is in secret and in the right way. So user guess is 4 and then secret is also required. So secret are both required. So each user guess, etc. We how many bits are enough to represent the user guess? I guess 4 bits are enough, right? Number 0 to 9. So I suppose we could keep 4 bits, right? So 4 times 4 is 16 bits, right? So we could say input. You could say like this. Okay. You could also do it like this. Verilog allows you to do like this also. Okay. This means user guess is an array of 4 digits. Each digit is 4 bits. Okay. So this syntax is also allowed. Then secret is also similar. Okay. So how do we proceed now? We have got the inputs. We have to generate the output is a feedback step. The feedback can be one of the three, right? It's either minus C or B. So we can encode them in 2 bits. So 0 0 means let us pretend that 0 0 means it's not there. 0 1 means it is there. It's a cow, and maybe 1 1 means so output is 1 to 0 of feedback string. Okay. So it is a uh, 4 cross 2. So we'll encode it as 0 0 means minus, 0 1 means cow, and 1 1 means 2. Now, how do we proceed now? We know what to provide. The input output is clear. Okay, we know how to generate the output. Sir, there is 4-digit secret, right? Yes, secret is a 4-digit number. So there are 4 digits, right? Each is 4 bits because we can have 0, 1, 2, 3 up to 9. This is 3 because I have 4 digits, and this is 3 because each digit requires 4 bits to represent. Is that clear? So what do we do now? Very good. Somebody has very correctly. Mihir Patel, excellent. Use comparator for compare number and another for index. Yeah, nice. So we could take. Let us take user guess of 0 and compare with all all of these. Let us say secret 0, secret 1, secret 2, and secret 3. And similarly, user guess of 1, same thing. And user guess of 2 also. User guess of. So we'll go ahead and compare, right? You could do it one by one if you wish, right? or you could do it all together. So if you do it all together, you will need 16 comparators. Okay. If you do it, you can do it with one comparator also. In which case you will do sequentially, right? You will do first user guess 0, secret 0, user guess 0, secret 1. So if you go like that one by one, you will need 16 clock cycles. If you are doing, so it's up to you. You can do all 16 in one go or one by one. So if you do one by one, you will do a sequential circuit. Right? If you do all at the same time, you will make a combination circuit. Right? As soon as user guess is given, boom, 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 it will give you the feedback spin. So if you compare, see what could happen is we may get this output. We could get 0 means no, it is not comparing, right? 0, 0, 0. This could happen. So what does that mean? If let us say user guess 0 is not there in any one of the places, that means the what is the feedback string for user position 0? The feedback is minus, right? Because it's not there. Whereas if it is there, let us say here, let us say it is, because we are assuming that it is unique, right? I mean, all the characters are unique. We'll have, it can, one of these will occur. And finally, 0, 0, 0, 1. Only these four things will occur, right? No, I'm sorry, one more is there. Why do I say that only these five things will occur? Because I won't allow repetitions in the feedback in the string. For example, it is not correct for me to guess maybe 4, 4, 5, 5. Okay, that is not allowed. In Wordle, that is not true. In Wordle, they allow repetitions, right? And as a result, the game is more interesting. When you allow repetitions, the guesses are more complex. So in the first case, what is the feedback? The zeroth character of the user guess was found in the zeroth place of the secret, right? So let us look at suppose the secret was 4967, and the user has given let us say 3495. Okay. So we have found this 3 here. So that corresponds to this case. It could also be 4, right? And 5, In this case, it was found here. Okay. User guess can also be um, 3649. It can also be 4563. So this three, okay, um, it could be in any one of these positions. Okay, I'm sorry, four. Four is here or here or here. So any one of these. So in each of these cases, tell me what is the output, what is the feedback. So user zero is present in the right position also. So here it must be 1 1. You agree with me? Whereas here it's a 0 1. Here it is a 0 1, and here it is a 0. Am I making sense? Is everybody with me? Or have I lost? Rohit Madlani, sir, as we are taking 4 digits of 4-bit each, then what if user enters 4 digits as 10 10? No, that is we in when we come to this module, it's all verified. Okay, maybe we can add that here. Okay, so maybe we can add somewhere that it should be where you read user input and validate. For example, if he enters anything all digits must be from 0 to 9. Okay, so it's a 4-bit number, but 1010 etc. should not be. So that is where your ease BCD will help. Remember, we generated one ease BCD. Okay, so you can use that to check if the user has given only valid BCDs. But do you agree with what I'm saying? So when I compare user guess zero with all these four, so one of these will occur. If it doesn't occur anywhere, then the user guess is wrong. If it is, if this happens, it is bull. In the remaining cases, it is a cow. In the same way, user guess one, all zero is minus. This will be cow. This will be bull. These two will be cow. So this BCCC will become CBCC, CCBC, and CCCB. So we could keep such an array. Akash, one more time. Okay. See, suppose my secret was 4963. Okay. If the user guesses 4580, that means user guess 0 was 4, and we hit it here itself. Okay. User guess 0 is matching with secret 0. Okay. That means, it must be a bull, right? So that is why I have written this. Whereas if the user gave 4 in the second in this position, then it will match here. Here. So the user has guessed the number, but in the wrong position. So we'll have to give the feedback as cow. Is that okay, man? Akash. Now, does this ring a bell to you? This this module, does it have anything to do with what we any other circuit that we have done today or yesterday? Yeah, that's right. The encoder, right? So you're right, right? So we have all these 4 bits coming in, right? And if not, it's like interrupts, right? So if a one is coming, that means it's like an interrupt, right? We know that in this example, since we don't allow repetitions, we will not have one, one, etc. But that's okay, right? So if all are zero, then we have created one bit which tells us that nobody is interrupting. So if that happens, the feedback is minus or 0, 0. If if an interrupt has been received, right, then we already know how to encode and if that encoded value is is the same position as this 0, okay, then we will generate a bull, otherwise we'll generate a cow. So I'll give you a little bit of time, right? Maybe a few minutes. So try to think about the logic and see how you are going to generate. You can do it with 16. Uh, you can have 16 comparators. So you are welcome to have 16 comparators. So if you want, you can even create a small module called comparator, which takes as input two 4-bit numbers. Okay, user character and secret character, and maybe the index. It depends on how you want to do it. Okay, there may be one solution which is slightly better than the other. See, you could also do it like this. You could say just will compare, and it only returns 1 or 0. So it's important for you to sit down with some paper and pencil and try to come up with some design. Okay, there may be many designs. Let us say this is user gets 0, and the same user gets 0 also goes out. And we have something similar here. So this is secret 0, this is secret 1, this is secret 2, and this is secret. and we could come up with a similar. This is user guess one. The secret in is also going out. Okay. So this is comparing UG0 secret 0, UG1 secret 1. I'm sorry, UG1 secret 0, and so on. UG2 secret 0, etc. And the result of the comparison will be sitting here somewhere, and we could take those guys to your what is that module? The priority encoder module. Let us say we have a small priority encoder here, a priority encoder here, a priority encoder here, and a priority encoder here. Okay. The result of the comparison, the four comparisons will be routed to this guy. Yeah, each of them is a 4-bit comparison. So I'm sorry, it is not looking so great. But what I mean is the result of the comparison 0 or 1 is coming here. See, if all of them are 0, then we know that, user, in the position 0, user has to give a minus. Okay. And if the index became 0, 0, then that means we should give cow, um, and so on. So there'll be one such encoder here. Right? The output of the comparator is 1 bit, 0 or 1. Okay? If the comparator will say it compares or it doesn't compare, right? So if the encoder module will get, let us say it gets 0, 0, 0, 0. That means, what does it mean? Means that UG0, remember this is UG0, user guess 0. Okay? This is secret 0. And this is secret 1, secret 2, secret 3. If all the comparators are 0, 0, 0, 0, that means UG0 is not present. So as a result, our feedback will be uh, minus. Okay. If it is a 0001, right? Uh, if it is 1000, then that means it is bull. Okay. If it is anything other than 0000 and 1000, it is a cow. Okay. So 1000 means bull, and anything else is a cow. Here, all zero is a minus. 0100 is a bull. Anything else is a minus. Here, all zeros is a minus. 0010 is a bull. Anything else is a uh, cow. Similarly, here, all zeros is a minus. 0001 means it is a bull. Anything else is a cow. We are not really doing in two steps. Okay, we are sort of comparing. Then the result is a combination. See, as soon as you give the user guesses and these secret values, all these comparators will act together, and the outputs will become available here, right? And based on this algorithm that I just mentioned, 0000 means minus, 1000 means so used on that, it will immediately produce the feedback string. Okay, the feedback string will be available. Yeah. So it's not a sequential circuit in the sense that we are not doing it one after the other. It's a combination circuit. It's expensive because we are doing, so many things. We have 16 comparators, right? And we have four of these encoders. So maybe it's a little bit expensive in area, okay? But then it is going to do it in combination. We don't need to have the hassle of designing a controller and all that kind of stuff. Okay? Any, you may have other designs, huh? I mean, this is not the only way. I mean, I'm just giving you one possibility. Okay? You could do it in so many ways. So the 16 comparator outputs, right? Let us keep them in some, reg or something like that. Reg 3 to 0 comparator output. So this is one way. So we have created a four 4-bit registers. So 16 bits. Suppose we create a module called comparator, which takes user guess, secret user guess character, secret character, and it takes that comparator output. So this is a very simple module. Right? Input is a 3:0 UG character and secret character, and then output is a 1 bit. And then all you have to do is comparator output equals UGC equals secret. If they are identical, you will get 1, otherwise you will get 0. So this may be a wire because it's not a register. We need wires. Yes. Everybody understood this? This comparator takes two 4-bit numbers, take two digits and compare. So maybe digit is a better idea. Okay, this I have given C as character, but it could be digit. So I'll need to put 16 of these. Okay. So see, it will be painful to write so many statements, isn't it? We have to write comparator 0 0 and send the user guess of 0, right? Secret of 0, and then what is it? Comp output 0 0. So like this, we have to write 16 statements. Okay. So there is a way in Verilog called generate. Okay. So you can write, if you don't want to write so many statements, you could say, I'll write a for loop, right? It will expand the for loop. So let us write genvar I and j. Okay. So these are special variables, genvar I and j. So what we have to do is for I equal to 0, I less than 3, I less than 4, I equals I plus 1. For j equal to 0, j less than 4, j equals j plus 1. Here we say generate. So generate, we will call it as comparator. Maybe we can call it comp. Comp is a name I'm giving, and the name of the, what is it called? I called it comparator. Comparator. The instance name I'll give comp. Okay. What it will do is it will add its own string to make sure that they're all unique. Okay. Because when we instantiate a comparator, you need to give an instance name. But when you do it in a generate statement, it makes them unique by its own. And here you may have to put I and I, sorry, I and J, isn't it? No, wait a minute. I give here user guess. I don't need J. I only need one, I think. The outer one is for, this will be J. Am I doing it right? See, for user guess, So when I is 0, it will compare it with 0, 1, 2, 3. When I is 1, it will compare it with 0, 1, 2, 3. Okay, and this will be I. Did I do it right? Just check. See, the outer for loop is meant for user guess. And each of them will be compared with for each secret. So when we are here, when I is 0, it will expand it as 0, 0, 0, 0, then 0, 1, 0, 1, then 0, 2, 0, 2, 0, 3, 0, 3, then 1, 0. Have I done it correctly? Please check. J, yeah, both are required. So what I'm doing is I'm doing this. This is I loop, I equal to 0, 1, 2, 3. And this is a J loop, J equal to 0, 1, 2, 3. For user guess I equal to 0, I have generated secret 0, secret 1, secret 2, secret 3. And the outputs of the comparators are that comp 0, ij, etc. Let me look at the chat in case anybody is asking some questions. Output is 1 bit, yeah. Did I make it? It's a 1 bit out. Yeah, it's only 1 bit. And we'll need some sort of an encoder. We'll call it module encoder, which takes 4-bit comparison outputs and gives feedback. It takes comparison status and feedback output. So the comparison statuses are 4 bits. Okay, we are getting 4 bits. Feedback output is 2 bits. So this module should maybe we should also take the index. That means with which index it is. See what I mean by index is this is the 0, this is the first, this is the second, this is the third. So I call it index 0, index 1, index 2, index 3. Okay. We'll take index also as an input. The index is a 2-bit input. Again, we will generate statement to for I equals 0, I less than 4, I plus plus. we need a encoder. Let us say we call it ENC. And what should we send? We should send uh, the comparator outputs of the stage I. Okay. So we should possibly write comp output. So I0 comp output I1 comp output I2 and comp output I. Correct? And we may want to bundle them together because we are treating them all as one 4-bit number. So you remember when I write within flower brackets, it sort of concatenates everything together. So it's better to write it like this. See, when you write like this, bugs are easy to catch. So the 0, 1, 2, 3, etc., if they are not aligned, there'll be bugs. Okay, you can. So what I meant by this is I have generated encoders, right? And this is the index 0. I think I have to give the index also, right? I forgot to give the index. So index is I. Okay, the encoder takes the compare status, index, and feedback out. So index is also one of the inputs. So in this case, I is actually an integer. Okay, but that's okay. It understands that it will send only 2 bits, and then the final thing is feedback out. We have to still create this feedback, right? So feedback will be another bunch of wires. So there will be 4 of these feedback guys. Each is 2 bits long. So here, what should I say? The module says feedback output, right? How do you get the feedback output based on this? If comparative status is 0, 0, 0, 0, we should say feedback output is 0, 1. I'm sorry, 0, 0. Okay. So we could create an always loop if you want. And if you write star, no, it will figure it out. Okay. So you don't have to explicitly say that it depends on comparative status, index, etc. It will figure it out. Okay. So we can say if comparative status equals 0, 0, 0, 0, then the feedback output will be we could let us try it this way. If you do it this way, we have to write as a range, right? Else, You can write maybe a case statement. Case comparator status. Well, we could have written the whole thing in student's case, right? Could have written the whole thing in case. So case comparator status and case, right? If it is 0, 0, 0, 0, then feedback output equals 0. If it is 1, 0, 0, 0 and index is 0, okay. So if you want, okay, if index equal to 0, 1, then feedback output equals 1, 1. Else feedback output equals 2B 0. Similarly, if it is 0, 1, 0, 0, if index equals 2B 0, 1, then it is same thing. This has to be copied. If it is 4B 0010, then same thing. If index equals to B 10, and lastly 0, 0, 1. See, we sort of know that nothing else will happen. I think there is a default also, right? There is a default that you can write. But this will not occur. It should not occur. So if it occurs, we'll put this 0, but that is a dangerous thing. It should not occur. If that's something is wrong with our code. But the advantage of giving that default is that see, then it generates combinational logic. Okay. It knows that we have handled all the cases. See, feedback output, suppose you are assigning only in some of the cases and the other cases you are not assigning, then it thinks that it should remember the feedbacks output from the previous assignment. So it will, it'll put some latch in order to put that value. So we have making sure that it is combinational. So now what they are doing is they have given always comb. See, this is only in system Verilog. Okay, that makes sure that this kind of a problem doesn't occur. Okay, so always means it's a system Verilog construct where if you forget to handle some of the cases, okay, you are saying that for 0, 0, 0 for feedback should be this, for 1, 0, 0 it should be this. But what if it is anything else? Verilog doesn't know that others will not occur. We happen to know. Okay? We happen to know that we will never have any other case because our encoder Either all the bits will be 0 because it did not match, or it will match in one of the cases, right? But Verilog doesn't know that this other cases will never occur. So it will try to remember the feedback output from the previous whatever was set earlier. So it will try to put some latches. Okay? I hope that point is clear. End instead of end module. Yes, you're right. Correct. Agile. They are very agile, man. There is one agile technology also now. You know that, right? Hmm. Agile Matthew. So we have generated the feedback for the encoders, and the output of this module is feedback output, which is I'm sorry, not this. Where is our original module? Okay, the original module has feedback string. Okay. Now we have to grab all the feedback of the four things. Okay, and that will be our output. So assign feedback string to be the feedback that you are getting from each of these cases. Feedback 0, feedback 1, feedback 2. So this flower bracket syntax means just concatenate them together. Each of these were 8 bits, 2 bits. No, this may not be correct now because the way I have declared it is like this. So I'll have to do it slightly differently. Assign feedback string of 0 to feedback 0, right? And assign feedback string of 1 is even this we could have put in the, since we are like doing like this, we may be able to put generate. Okay. So generate and put a genvar. And generate. So generate simply means I don't want to write all those statements one by one. It will be too much. You can do it if you want. If you have the patience, you can write all the 16 statements. Nobody is going to object. But if you want to make your life easier, you can do it. And you will also probably create less bugs. Okay, when you write 16 comparators, somewhere you may make some mistake, and it will be very difficult to debug. So once again, module give feedback, takes user guess and secret, and produces the feedback string. User guess has 4 digits, each of 4 bits. Okay, 4 digits, each of 4 bits. Example, it could be 4, 5, 6, something. Similarly, this is also same thing. may complain if I don't this feedback I may have to first declare. No? See, some compilers don't mind, but you have to first declare this. Otherwise, it will say I don't know where this. So it has to see this feedback first. Then only you can use it. Otherwise, it will say I don't know where it is. Hmm. So we declared 16 comparators, right? The first one compares user guess 0 with secret 0 and produces comparator output 0, 0. Second one compares 0 and 1 and so on. And the outputs are in this array of wires, comparator output IJ. And these are going to the encoder. So I have 4 encoders. To the first encoder or the 0th encoder, I am sending this comparator 0000110. I'm sorry, 0203, 1011, 1213, etc. And that will produce feedback 0. Okay, and so on. Okay, let us see if this compiles. We have to choose maybe iCarus Verilog. iCarus Verilog is a free Verilog, whereas the others you will require. Okay. Syntax error at line 12. This should be red JB, no? Or this should be assigned. I'm sorry. This should be assigned. Okay, that is one error. And 18 syntax error. This is actually the output red JB. See, after every change, you have to compile. Otherwise, it's 22. Unbased system verilog literal cannot have a size. Oh, what is that mean? Let's see what is wrong here. Based system verilog literal. See, I think this is B. Okay. So look at the, it gives such a confusing error. 33. Array dimensions in complete port declarations are currently ignored. What is that, man? 33. Array dimensions in complete port declarations are currently ignored. Oh, 60. Error I has already been declared. 60. Because I is possibly already there. Genware is only there. So frankly speaking, Verilog should not allow. See, this should be Genware IJ here. If you are using a pure system, pure Verilog compiler, it will not allow you to declare Genware somewhere else. After you have to put it here. This guy is actually treating it as system Verilog. Comparator, I have not declared correctly upon. Comparator, it is comparator, it is comparator. Let me see. Port 1 of comparator expects 4 bits, got 1. Oh, what is that? Hmm. Comparator I0. What I declared is what is it? Feedback string 2 is out of range. Huh? Port 1 of comparator expects 4 bits. User guess of I, is it not 4 bits? User guess. Just a minute. Let us. Let me try this in Cadence and see. Hmm. Into feedback, I undeclared identifier 26. I think it is small bit. Feedback is small. See, I think that ICAR's Verilog compiler is a little bit, it didn't understand everything we're trying to do. Whereas this Cadence guy seems to understand. Give feedback. I port sizes differ. Yeah, this I we assembly, no? So we have to do something there. So how to do this? Can we say I is an integer? So maybe we can say 1 to 0 or something. That means See, this guy went through. I mean, it is understanding correctly. Okay. I don't think your accuracy is not able to understand. I don't know what it is, why it is confused. You see, it's confused. Somewhere warning, somewhere errors. What are the errors? Let me also try this in our tutorial point very loud. Let us see what compiler they have and whether I can get it to work there. How to how to move this guy? We can come back in a couple of minutes. Huh? I'll need a so this thing not able to connect. Just mm. Sorry, guys. So if I can give you this file, but I don't know unless you have access to Cadence, you may not be able to do it. This guy is not understanding the. Okay, let us go ahead with I Cadence for a minute, and we'll write a test bench. Okay. So module give feedback test, right? And we'll have to instantiate one copy of feedback. For that, we'll need user guess. Reg v:0 user guess, then reg secret, then feedback string will be 1:0, and so we'll instantiate give feedback as a module, and let us say instance name is GF. And we'll bind UG SWFB. And initial, we'll try UG 0 is, let us say, 0100. This is 4. UG 1 is, let us say, 5. UG 2 is, let us say, 6. And UG 3 is 7. So the user has guessed 4, 5, 6, 7. Okay? Whereas the secret is, we can try 5 outside 5, maybe 0000. SW2 is 4B. So here is and let us try 6 and SW is so if things go well, this 5 should give me a cow, okay, because it is in the wrong position. This should give me a blank. This should give me a bull, and this should give me a cow. I'm sorry, minus. Right? So after everything is done, you have to give 1 unit of time, then display FB of 0, percentage, percentage. We'll give it a try and see whether it goes through. So the first one was 0101, right? So I don't know why. The third one is correct. The third one is a bull. The second one should have been 00, right? So there is some error. The last one is 00 is correct. The second one should have been a 00, and this should have been a cow. So 9 is not there, correct. 6 is a bull, and both the previous, this is correct. This is correct answer. Okay, this is the correct answer. Let us try all 4, 5, 6, 7. I should get all bulls. That's okay. Then maybe I will make this 9, 0, 0. So it should all be minus. Everything should be minus. So it seems to be okay. I think when I gave the first test, I think I didn't give correctly. So it's better to give it in digits. Then we can see what is going on. But okay, guys. To test it thoroughly, you may have to create a lot of test cases. Like uh, the first should be a. Okay, let me ask you guys. What tests will you run, man? Yeah, I'll give a summary of it. I'll give a summary of it. Okay, once more. Dave is asking. So here is a summary. So we designed a. We have 16 comparators. Each comparator produces the comparison between. So this is, I'm going to treat this as I equal to 0, I equal to 1. So the columns are I as far as I'm concerned, and rows are J's as far as I'm concerned. So user guess 0 is compared with secret 0, secret 1, secret 2, secret 3, right? Similarly, user guess 1 is compared with user guess 0. I'm sorry, user guess 1 is compared with secret 0, secret 1, secret 2, secret. User guess 2 is compared with secret 0, secret 1, secret 2, secret 3. So we will get 16 results. Okay. Now the 4 of these results, okay, it will tell me whether user guess 0 is present or not. So in this example, I may have given, let us say, UG was 9485 and secret was 4687. Okay. So this is what I have given. Okay. Now this 9 is going to all these guys. And I'm getting 4 here, 6 here, 8 here, 7 here. So 9 will be compared with 4. The answer is, it's not comparing. Here also 9 and 4 don't, 9 and 6 don't compare, 9 and 8 don't compare, 9 and 7 don't compare. So 9 is compared with all 4. So I got 0, 0, 0, 0. Now that is going to the encoder. The encoder looks at the case 0, 0, 0, 0, and the feedback string will be 0, 0. In this guy, this 4 is being compared. So 4 and 4 are compared here, and I will get a 1, right? And here, none of the others will compare. So I'll get 1, 0, 0, 0. So 1, 0, 0, 0 means it's a cow because, I'm sorry, yeah, it's a cow because I'm getting the comparison in this guy. If the comparison is along a diagonal, see if user guess is matching the secret 0, if UG 0 and secret 0 are matching, that means it's a bull. So the diagonals correspond to the bull. If all are 0, it's a minus. If any non-diagonal is a 1, that means it's a cow. Is that okay? There. So what? Go through the design again. So we have a comparator which takes a user guess character. The user get character is a 4-bit number, like 1000, etc. Similarly, secret character is also a 4-bit number, and it gives me the output of the comparator. So comparator output is 1 if these two are same, 0 otherwise. It's a simple assignment step. Similarly, the encoder gets 4 bits of comparison. It also finds where the encoder is. That means am I referring to this encoder 0 or encoder 1 or encoder 2 or encoder 3? That is the index. And it gives the feedback out. Okay. And then what is happening is it looks at the comparison status. If it's all 0, then the feedback output is minus. Okay, that is 0, 0. There are 4 cases: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0. Now, the output depends on the index. If 1, 0, 0, 0 is coming and the index is 0, 0, then we have a bull. Otherwise, we have a cow. Similarly, if the index is 1, then the feedback is bull. Otherwise, it is 0. I'm sorry, cow. If the index is the third one, I'm sorry, second one, then bull. Otherwise, cow. This is the last one. Index is third, then the feedback is 1, 1 or bull. Okay. So we have encoders and the comparators. This is the main module. It takes as input a 4-bit user guess, 4-digit user guess, and a 4-digit secret, and produces a 4 character feedback string. Each character is 2 bits. And 0, 0 is minus, 0, 1 is cow, and 1, 1 is bull. Right? We'll need 16 comparator outputs. Okay. So there are 16 wires. These correspond to I, these correspond to J. Similarly, feedback, we'll need for each of the encoders, there is a feedback. Okay. Then this feedback string is nothing but the feedback I provided by all those encoders. Okay, the encoders produce the feedback. I'm just assigning them to the output. Okay. I could have possibly directly given feedback string here. Okay, there is no need to do the way I have done. I could have directly connected the feedback string way itself. That could have been done. All right. These are the 16 comparators. We use the generate statement. What does the generate statement do? It sort of unrolls the loop. Okay, instead of having to write 16 comparative statements, we are writing two for loops. So it will unroll the for loop for both I and j, and it will generate 16 comparative statements. In the first one, it will write user guess 0, secret 1. I'm sorry, user gets 0, secret 0. User gets 0, secret 1. User gets 0, secret 2. User gets 0, secret 3. And the compare outputs also will be 0, 0, 0, 1, 0, 2, 0. So like that, 16 comparator outputs will be generated. And we are generating another generate statement. We are giving another generate statement. Here only one for loop is there. So 4 encoders will be defined. Each of those encoders will receive the comparator outputs for the corresponding column, and the index also is passed. See, index is because is I is a genvar, it may be an integer, so we have to only look at the last 2 bits. So this is the last 2 bits. It gives an error if you don't do it this way. If you directly send I, it is not, it gives some problem. And feedback. To test it, we have created this UG and SW, user string and secret, right? This is an instance of this give feedback, right? And I have created only one test case, but we could have created many more, right? We could have written that u random range, right? We could have written maybe several test cases where we generate random numbers in the range 0 to 9 as user guesses. Secret we can keep same. The secret we can decide once and for all, and then change the user guess. So hopefully all the corner cases will be generated. Okay. Now the question to you is, what would be adequate testing? What are some of the verification tests you will do? Where do you suspect, there could be problems? You understood? Let us say this, you are not the designer. Some designer has generated this give feedback, and you are only supposed to test it. I mean, verify it. So how will you verify this give feedback? What are some tests you have to do? So give me ideas, no? See, the problems that may be there is maybe the feedback string is wrongly generated for. See, we have to make sure that every position we get minus cow and bull, isn't it? If I manage to get a minus cow and bull in each position, then I know that it's fairly okay, right? Otherwise, there is some problem here because of which that bull never comes. Okay. You have to try to get the BBBB case, that means all bulls case. You have to try and get the CCCC case, right? Why do you say that 4D? It should be 4, man. This notation means 4 bits, right? And I am giving the information in digital form. Okay. So they 4 4 code D means it's a 4-bit number and I am giving it in decimal form. Okay, it doesn't mean that I am giving one digit. Understood? It's wrong to put one here. Understood? So you have to write test cases. That part I am going to give you as a exercise, right? You have to try and torture this design and throw all kinds of test cases at it, right? So you can keep 4, 5, 6, 7 as a secret and try different cases. Okay, in this case, all are minus. Okay, then we can try whether the first one cow will come, second one cow, third one cow, right? You can also do exhaustive testing if you want. You can try all the 4-digit numbers. So there will be about how many 4-digit numbers are there with no repetition. The first one can be chosen in 10 ways. The second can be chosen in 9 ways. Third one can be chosen in 8, and the last one can be chosen in 7. So 10 times 8 times 7 times 10, 9, 8, 7. So 10 cross 9 cross 8 cross 7 numbers. So you can write a for loop and generate all the combinations, number one. And then you can use your own algorithm, which you can, you know what to expect. So the verification engineer also knows what to expect. This is being done in hardware, whereas this guy is going to do it in some like a software programmer he will write. His job is to only the design. See, frankly speaking, the verification engineer doesn't do this. Okay? He only writes the test bench, right? But I have to illustrate this for you. Okay, so that is why. See, if I give you some random design and say I'll only talk about verification, all of you will get thoroughly bored, right? You don't know anything about the design, right? You will get bored and log out. Mhm. So I'm going to give you that too as an exercise, right? Generate all widgets or all user guesses. That means 10 times, 9 times, 8 times 7. That's a fairly large number. Okay? And ensure the outputs are correct. So the verification engineers may even sort of write things like tasks, etc. Okay, so I can write a task or a function. So it's like a software function feedback string. It takes UG and SW. Okay, UG is a reg 3:0. Both are the same. What is a function? A function, uh, takes us. It's like a C language function. It takes UG and SW as inputs and produces the output. Let us say it produces 1:0. Okay. and UG is a input. So here I can treat it like a software thing. So I can write maybe int ij and all that. For I equal to 0, I less than 3, I equals I plus 1. Okay, that means for each user, for each character in the user string. What I have to do is I have to search. If UG of I equals SW of J, okay, and I equals J, that means the indexes are also matching. Then we have a bull, right? Then what we have to do is maybe we can keep on else if UG of I equals SW of J, that means it matches, but it is not the right position. Then we can say out I equals 2B 0 1. That is a cow. If neither of them is there, then it must be UG is not there in SW, so you have to give. Right? So let us do this in Python or something like that so that you understand what is happening. They have a definition called feedback. It takes user guess and secret word. So we'll do for I in range 4 or J in range 4. Right? If UG of I equals SW of J, right? And I equals J, then return bool, not return. UG of I equals SW of J, then feedback spring of I equals C. Then return at this point. We have already initialized it to minus minus, so if nothing happens, we'll just leave it at this. Right? So if you compile this guy, feedback, UG is 4567. The secret is 7490. So it gave me this cow. Okay. 7 is a cow, 4 is a cow. Okay. So this is what I meant. See, this is a very high level software program. Okay, we have all kinds of facilities. We can have a list, right? And so Verilog, or I would say system Verilog, is leaning towards this because see, this is so much easier to write. You understand? In pure Verilog, if you have to write a verification program, these kind of facilities are not there. So people prefer to use something simple like this. As a matter of fact, I think that is how the future trends are. They are trying to use languages like Python, which are so much more easier to verify. See, remember the verification engineer has to implement a spec kind of a thing, right? See, he also knows he or she needs to generate the outputs for a given UG and SW, right? And if possible, using a different algorithm, right? This verification engineer doesn't know how the hardware has been implemented. So he figures out some other way to check whether what the feedback should be, right? And then he checks whether the hardware is giving the same answer. You understood? Are you guys following? I'm worried that you are not following. I'm not seeing any feedback. Only Dev is giving me feedback. See, this is a, if you didn't understand this Python program, don't worry. Okay, if you don't know Python and you didn't understand, don't worry. I just wrote a simple program which takes two user strings and gives me this cows and bulls. Okay, this is somewhat high level. It is not like hardware. Okay, the hardware will need comparators, encoders, all that kind of stuff, right? But the verification guy, he doesn't have to design all those encoders and all those kind of things. So the verification engineer will use a high level language. So system Verilog is one such language. Okay. It is little better than Verilog. Earlier people used to do only Verilog. Okay. So as a result, today people are trying to lean towards things like Python. System Verilog is slightly better. Okay, in fact much better than Verilog. Okay. Earlier people used to write a lot of code just for verification. Okay. And see, it is counterproductive to do that. The more code you write, the more bugs there may be. So imagine that there is a bug in this program, right? And then I'm trying to verify the hardware and I'm complaining that it doesn't work. But the reality is, the verification program has a bug. right? So the verification language, okay. So there is a HDL, hardware description language, and there is an HVL, or a hardware verification language. So system Verilog is a hardware verification language, and you can use things like Python, C, C++, etc. also if you want. But see, for it to really be a hardware friendly thing, right? Maybe it's better to use something like System Verilog, because maybe you want to see waveforms and things like that. Okay, here I can't see any waveforms, etc. Right? But sometimes people want to see waveforms. All that we cannot support here. Okay? But if your interest is in sort of verifying the functionality, right, by looking at maybe textual output like this, right, and then complain whether it is correct or not, then you can use System Verilog, maybe even C, Python, etc. etc. Is it clear to people? If Python program has very few, why did we do? Okay. So Abdul Rahim is asking, if Python program has very few lines, why did we do these in System Verilog? Okay. Yeah. See, you are absolutely right. Okay. If we could have a Python package for verification, we will use that. Okay. And that is where I think people are trying to do. Okay. So System Verilog is like it has been there for a long time. See, it's been around for maybe like 10, 12 years. Okay. So it won't be easy to displace it. Okay. Maybe, people will slowly move to this Python and other things. You understood? So you're absolutely right. You want it to be simple like this, right? Dave is asking, sir, is VLSI done in C? Hardware C used to be there, but I don't think it took off. Okay, hardware C is not, to my knowledge, nobody uses it, right? Verilog is still very popular for design because you can take it to synthesis. You understand? If you are only interested in verifying, you can use things like hardware C, etc. But finally, you need the actual chip, right? So Verilog, VHDL, they have all those tools. Okay, your Cadence tools will understand design done in Verilog or VHDL. Okay, so it is still required to do Verilog or VHDL. Okay, any question? But you ask good questions. I'm impressed. On what else? What is Pujita asking? Sir, if the comparator module declared takes two inputs of 4 bits, but for instance, the two inputs, for the instance, the two inputs give one. Yeah, I mean, it compares the two 4-bit numbers and gives only 1 bit, whether they match or not. Is that clear, Pujita? We compare the two 4-bit numbers and generate only one output. They are matching or not matching. So is the summary of the design okay with you guys? Okay. So this was a little ambitious, right? We defined a problem, right? And then we sort of wrote the design, right? Then I also explained how you can verify this verification test bench. You can improve. Okay. Right now, I have done it in a certain way, but what I was trying to explain is just like I was trying to write that Python. See, you can see that This one is also not so friendly. See, Python was so much more easier, right? But here I had to do a lot more work. Okay? But you can write this function and use it in that code. Okay. A little bit more, these guys who developed Verilog, they were inspired by C language. And those who developed Verilog, system Verilog, I think they were inspired by C++. Okay. So maybe in the future, something based on Python will come. Maybe already, I think people do some of those things. And see, people will not immediately switch now because you have already been using this, and it's not easy to convince people to suddenly give up everything. And okay, so that is, it will take time. Is that clear? Abdul Rahim, are you convinced? Abdul Rahim, are you convinced? No. Yeah, I mean, keep on the lookout. I mean, that is what these startup companies do, isn't it? They will come up with a solution which is better, and it will take time, but finally it will get accepted. See, even system Verilog, it took a long time, right? I mean, people were not willing to give up. See, it took a long time for them to give up VHDL, right? It took a long time for them to give up, Verilog and move to system Verilog, right? So that inertia will be there because a lot of, see, you can also create what is called as verification IP. Okay, where just like IP is created by people, okay, there is an IP for cache controller, DMA controller, etc., etc. For verification of these also, people can write test benches, etc. Right? They will have this kind of function, task, etc. And that also is, people will buy such things. Okay, because see, suppose I am, in a company and I have decided to use, there is Abdul Rahim is selling some USB controller or something like that, right? And I don't know. I mean, I'm just I'm going to use it, right? I have no idea how it is done inside, etc. I have no clue, right? But I want to verify it. Okay, so either I can employ a verification engineer and ask that person to check if Abdul Rahim's USB controller works correctly, whether it has some bugs, etc. Right? Or I can also buy somebody's verification IP. I can go to Dave, and Dave may be selling a verification IP for this USB controller, and I can put them together and check, right? So people are doing such things so that they can be, they can move fast, right? You have to understand that everybody cannot do everything, right? The USB controller I had to put in the chip because customers are asking for it, right? But that is not my expertise. Okay, I may not at all be conversant with USB, but it is a requirement. So why should I, either I employ, several people to do USB design, USB controller design, spend many months, right? But people will they hesitate to do that. It's very expensive. So they will rather look around and see if there is already a IP somewhere. And even for verification of that also, maybe it is easy to go and get a verification IP. Okay. Ashwini Kumar Mishra, we should switch another tool which support Python. Yeah, man, you are right, but it will take time. Right? There are some. Okay, maybe if time permits, I'll try and towards the end, I will try to go and do that. What else? So it's about 9:40. So I didn't get time to write this function, etc. Okay, but I can show you the function in a. Let me do one thing. I don't want to mess it up by putting this. Okay, let me give this to Professor Vinis Savla without this. This is the plain and simple test bench. Okay, there is nothing fancy here. I want you to work on this and fix the. So the assignment for you guys is uh, fix this test bench to thoroughly test. Okay, either exhaustively or you can be intelligent and say, look, I only need to do these many test cases, right? That is where the sort of contribution of the verification engineers is, right? You can't do exhaustive. In this example, maybe it will not take too much time. Okay, uh, this may be around maybe how many is this? 10 to the power 4 approximately, right? About 10,000 cases will come, and 10,000 cases nowadays, this may not take too much time. It may get over. By the way, these free websites, if it takes too long, they will throw you out. Okay, if you write a very heavy verification test bench which takes hours together, they will not allow. They will only allow you to run it for some small amounts of time. It's meant for learning. Okay? So don't be surprised if you try to write an exhaustive case like this. Maybe this guy will throw you out. And the other problem you might face is this guy may not, this Icarus is not understanding. Okay, it is complaining. See, there are some limitations of this free Icarus Verilog. Okay, even when you do system Verilog, you will realize the entire system Verilog is not supported by this Icarus Verilog. Okay, so if your college has Cadence tool or Synopsys tool, you can try to use that to make this work. Okay, or you will have to rewrite it in a way that Icarus Verilog will understand. There may be a small, we have to figure out why this guy complains and see whether there is a workaround. Okay, so everybody should understand that tools are not the same. So there are many tools, and the industry tools like Cadence, Synopsys, and this Mentor Graphics, since they have existed for many years, they are almost the same, right? They have similar capabilities, right? So there may not be too much advantage of using one or the other. They are all very similar. But if you see the freebie ones, like the one which your tutorials point has, or the one which this EDA playground provides, with Icarus, Verilog, etc., there will be some difference. Okay, one may be slightly better than the other. I tried to get that tutorials point to run this, but it was giving me some server timeout or something like that. So please try it out. Okay, and if you know any others, I think there is one more. There are some more online compilers, so you can try if any one of the others works. Okay, this is how it works. Okay, the tool also is not perfect. Even the commercial tools, okay, they're not perfect. So sometimes they will give you these kind of problems. So then you have to find some workarounds. You understood? It takes time for you to go and complain that this is not working and then get it fixed. It may take some time. So meanwhile, you have to get uh, an alternate solution in place. Is that clear? Okay. So let me give today's output to Professor Vineet Sahula. This is yesterday's. So this is your test bench, day 3. What is it called? This cows and bulls. And you can also try and see whether you can complete the game, right? Today we only did the feedback part, okay, which is the hard part. But you can also see whether you can do the other things and get it to a complete shape. That is the immediate thing. Okay. Any questions before we conclude? I don't want to start anything new. I'll let you go a little bit early. It's 9:50 or so. Any questions? Okay, good. So we'll break and we'll meet tomorrow. Okay, bye.
Thank you very much, sir.
Let me give it to Professor Vince Bula. Good night, guys.
Thank you, sir.